When I had a Samsung, it would stop at 1 hour exactly. So now I squeaked 27 minutes and some seconds out of this one, a little bit more. So, what do you think would happen? So here's the original. That's an area. How should that change that area if I just multiply that by C? So if I had a box that was 1 foot wide and 8 foot tall, what's the area? 8. It's amazing. So what if I double the height? Area is going to double. So I could put a 2 here, or I could just put a 2 on the area. So this should be this many times what the area would be. So if I just multiply the height by something, that actually just multiplies the area by that same thing. Another way to look at it now, I can talk about it as areas, but now I can just say any constant to just come out of the interval. Which only makes sense. The interval is an infinite sum. If that's a constant, it's just GCF. I'm just factoring out the C. Okay. Factoring out the C sounds kind of neat. So what about this here? Let me give you a little bit of background to this here. So let me tell you what's going on here equals what. So I have from A to C to B. So I'm integrating from A to C, and then I'm adding on top of that the integral from C to B. How should I be able to rewrite that? The area from A to C added to the area from C to B is just better known as the area from A to B. It's almost too silly. So you can just put this as one interval. Seems very simple, but later in this semester we'll see. Right now we'll see why this is good to know. If I have to find the area of this triangle, and I'm not letting you use geometry, I'm forcing you to use integration, what happens right at this point? So how would my f have to be defined in order for this to work? It'd have to be an absolute value, but really at the heart, an absolute value is more generally a here, but what kind of function is it? Piecewise. So I'd have to integrate from A to C and then from C to B, because I'd have different functions. So the integral from A to B of this function, to even be able to do it, I have to break it apart. Because the function looks different depending on what side I'm on. So that's really the way this works. This very often is used in reverse. Because you got something weird that happens at the point C. So I've got to break my integral up so I can handle that weirdness at C. So we use this in reverse very often in calculus. Okay. Whew. Okay. Blah, 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 blah. Okay. So the last thing I want to talk about tonight, and it's, good. It's, I can't give it any more importance than just to say the name. It is the fundamental theorem of calculus. You really can't add, and you don't need to. It's the freaking fundamental theorem of calculus. And there's two parts to it. And this is finally going to do what I keep teasing you with, that easier way of doing things. And the fundamental theorem tries to tie these things together officially. So everybody got stuff up here? No. All these things are in the book too. Let me do this. Okay. So let me first build up to this. We're going to build up to the fundamental I don't like the word banana. You're like, where am I? Theorem of calculus, which from now on will be known as the FTC, Federal Trade Commission. If I have this situation, now first off, we all know what this, well, let me see, let me be careful. We all know what this means. You tell me that represents what? Area from A to B under that f of x. I like it. But the thing that I could do now, some of you guys, I don't know if anybody's ever realized this, but if I have an A and I have this function coming along, and I actually don't know how far I want to go. One day I might want to go this far, and the other day I might want to go that far, whatever. So I want that second piece to be variable. So I can actually then define a function, g of x, let's call it. A of x would probably be better, but g of x is okay. That represents the area from A to some arbitrary other point. It could even be a point back here. I mean, x isn't really, the domain is not really tied down there. You with me? Now inside I can't have x also. So I have to have some dummy variable in its place. Okay, I'll let you absorb that for a minute. So the only thing we've done is instead of the, t is still a variable, but the real variable that this function is interested in is the variable x. This f is itself some function that varies as t changes, but g looks at it as that whole damn function is there. It's set. I know that when t is 5, it's 7, and when t, who cares? What I'm really interested in, there's the picture, there's the function. What's the area from A to some arbitrary thing? That's exactly what this function. So if I plug a 7 in, it's going to be, this area. If I plug a 2 in, it's going to be this little tiny area, right? So we're going to get all these values out for this function. So, let's see how much of I messed up my picture here. Let me redraw this picture. So if I have from A to X, and I have this function, doing all its weird stuff. What I want to know is, so this is a function. What do you think about this function's properties? Is that function itself going to be continuous? Considering, what does this function do again? As when x is a, so what's g of a? 0. And then if x is a plus 1, it's going to tell me the area of that piece of it. You with me? That chunk and so forth. So, this function ends up being, if you can remember that, this function, in order to be integrable, it's got to be continuous itself. And actually, we're going to get more into what integrable has to be. There's actually another way to get around it. But one of the best ways to have an integrable function is for this to be continuous. But this guy is certainly going to be continuous. It's just going to keep picking up more area as it moves along. Right? If I change x from 0 to 1 to 2 to 3. Now I'm curious about, well, what's this guy's derivative? Can I find this guy's derivative? So I've established a function that's built on an area of some other function. It's kind of neat. So I can do all the process we did earlier for this being from 2 to 7. And then from 2 to 8. So that would be g of 7, g of 8. Okay. So now I'm curious, what the hell would g prime of x be? And this is the first step to establish that link that we want to be true so desperately. We want the antiderivative to do what it seems like it does, to be the thing that leaves me out from having to do all that summation business. So if I can establish that g prime is something nice, let's see where we can go from this. So how do I do derivatives? What does a derivative really mean? So now we have to revisit this a little bit. We're not going to do, well, let me not say anything that's not quite true. Well, it's not going to be nearly as heinous as when we first talked about derivatives. We just got to remember a little bit about how we went about it the first time we did derivatives. How did we first talk about derivatives? I have my function, and if I want to know the derivative at that point, how did we figure it out? Yeah, if I want to know at the point x, I went a little bit away and went to x plus h, right? And I love it when you draw so small, you can't even see what. So, and then I can have that, and of course I let those get closer and closer and closer and see what happens, right? And you're going to end up with little arrows pointing in the right direction. So I'm going to do the same thing with this. So I'm going to go a little bit past there. I'm going to go to x plus h. And I'm going to say, if I do that, how much does this area change by? So g of x, where's g of x on that picture? It's kind of difficult to describe, but where would I shade for g of x? Between a and x. I love it. Right? So g of x would be this much. And so what is this? Nothing major. What is that? No, don't overthink it. If from a to x is g of x, what's from a to x plus h? G of x plus h. Cool. I like it. Some of you guys are trying to get ahead of me. That's all right. Certain questions you're like, I don't know what you want from me here. So what do I get? Now, so this might look familiar. And this is what I meant earlier when I said it's not going to be anywhere near as heinous as what we did when we first did derivatives. What would g of x plus h minus g of x be? That, of course, would be the part that you thought I was going to start with, maybe. That's the part, that's that here, right? Well, how big is that? How wide is that? H. How tall is it? Remembering that we're going to let h go to 0, it's g of x tall. I'd want to use that endpoint because I'm going to let h go to 0. So the x plus h part is going to go to x anyway. So how tall is it? It's g of x tall. So what's the area of that piece? I love it. So it's h. Get out of there. Stop it. Times g of x. So then, g of x plus h minus g of x is approximately equal to, oh, and of course, what did I just do? I got to be careful. Not g. I'm being silly. What function is this? What's the black function? What is it? Yeah, that black function is f, right? So how tall is it right here? F of x. Good. So it's h times f of x. G is the area function. It collects all the area. If I want to know how tall this thing is anywhere, I have to use the f function. Are you with me? So I kind of got lost there myself. Otherwise, of course, this whole thing goes to shit. I didn't want it to go to shit. So g of x plus h minus g of x is this area, but we just said that that area is h times f of x. Approximately, because isn't there like a little bit on this side, maybe it goes up a little. There's a little bit of either it's too little, too whatever, but it's approximately equal to h times f of x. What happens when I divide by h? Should look very familiar. And what am I going to do then? What I said earlier, I'm going to let h go to 0. So if I let the limit as h goes to 0 of g of x plus h minus g of x over h, which is the limit as h goes to 0 of f of x, and that's of course just f. The h is canceled here, right? I divided by h. So what is this the definition of? Derivative. So this is g prime of x equals f of x. Now, there are little problems with the proof that are actually taken care of by that limit. So if you look up proofs of this, they're going to make a big deal of the little extra piece that's here. But whatever little extra piece is there, if it's too low or too high, it's going to go to 0 in the limit anyway. So why worry about it? But if you're interested, you should Google fundamental theorem of calculus proof and see what happens. Right? This is huge. You don't even know yet how huge that is because I haven't told you how huge that is. You're looking at it like, ooh. But what does this really mean? This means that the let me see. before I say this, let me show you something silly here first. A real quick side note. That actually has something to do with that. Don't worry. What is the derivative of x cubed?
Derivative of x cubed?
Yes. 3x squared. So now I can say that x cubed, since its derivative is 3x squared, x cubed itself must be an antiderivative of, we haven't yet tied this together, an antiderivative of that guy. Except, of course, for that plus c. You with me? But this is basically a possibility that that's an antiderivative of that guy. How do I check when I find an antiderivative? I take the derivative. So if the derivative of this guy is 3x squared, that means that this guy itself is an antiderivative. So if the derivative of the integral, remember the g of x is the integral. If the derivative of the integral is f, that must mean that g itself is the antiderivative of f. All right, you still don't know what that really means. I know, I can see in your faces. But basically, I've just arrived at the place I said earlier we would get to eventually, which is this integral, the integral of f. It ends up being an antiderivative of f. That's the connection. And some of you guys came into this class maybe knowing that already. Maybe you've seen some calculus, or you've had some calculus somewhere else, or whatever. Let me try to really get it at you. G of x must be an antiderivative of f of x. Go ahead. So far we see this symbol, and I made it more clear earlier just in case I made a mistake and said something else. We so far know that this means the area under this curve from here to here. That's what that represents. The integral represents an area. We saw, of course, Jeff had to show you some examples of how antiderivatives actually get us there earlier and quicker. But now we've established that, yes, this guy, the integral, is an antiderivative of f. So not only is the integral the area under f, the integral is an antiderivative of f. They are connected. So we've got that connection established now. Kind of cool. I can see some of you guys are like, okay. So let me do part 2 of the fundamental theorem, and then we'll step back and see where we are. Here, part 2. Oh. So part 2 says if f is continuous on AB, and remember, the big ass F just means F prime is F. So really, now that we've got this established, the proof of this is pretty simple. And it's on, so part 1 is on page 388, and they talk about the proof there, and you can see all the mess they go through. And then part 2 is on page 391. And they go through a little more than you have to here too, but oh well. Blah, 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 blah. So we know from, so a really quick proof of this. We know from this that the integral of f of t dt equals g of x. We know that g prime of x equals f of x. So we know that g itself is an antiderivative of f. So how does big F and g, how do they relate? Well, what was missing from this discussion, you guys pointed out? When I said that that's an antiderivative, it was an antiderivative, except it was missing the plus c, right? So f and x differ by C. So this, F and G, they differ by C. So this is this G, which is related to f of x. It's just off from f of x by a constant. How are we doing so far? Is that decent? And we knew that earlier. We knew that was missing. You guys pointed it out to me. Well, that C is missing. All right. So if, and actually I could be a little more, well, let's go with this. If, so G of x represents from A to x, that area from A to x. Right? So if I want to know the area from, let's see. What do I want to say? Well, this will work out. I can do this. So I want to know the area from A to x. Oh, how do I set this up? Not that way. Oh, okay, that'll work out. You can do it the other way. So for example, f of x is basically g of x plus c. There's the antiderivative. Missing a c. So if I add a c to it, that's basically what that is. So if I want to know the integral from a to b of f of x dx, well, g of a would be what? 0. I love it, right? Because it's a to x, so if x was a, there would be 0. What's g of b would be what? G of b, of course, would just be this thing, right? So g of b, let's see which way I keep going in circles. I want to connect it. Oh, that's what I'm doing. Okay. I gotta go from reverse. All right. My bad. I had a way I wanted to do this, and then I turned it around. Let's do this in the reverse fashion. Let's say, what's f of b minus f of a? That's much better. So what's f of b minus f of a going to be? So we're going to kind of look at this in reverse. We're going to say, what's that equal? And show that it comes back to this. So what's f of b? G of b plus c. And what's f of a? G of a plus c. So now we can use the fact. So I was trying to build it the other way. It was easier to start with that side and go back and prove it the other way. So then I get, of course, g of a is 0. Because now I just have an a here. Are you with me? G of x, don't forget, g of x is just a to x. So g of a would be 0. Where am I at? Oh, and g of b would be this. So then I get f of b minus f of a equals the integral a to b. C's cancel. G of a is 0. So then I've proven that, of course I screwed it all up by going backwards first. But I've just established that the integral, this thing that used to just mean the area of under the function from a to b, now is equal to the antiderivative evaluated at each endpoint. So if I show you a concrete example, you'll see the power of this. Because, in fact, let's do exactly, well, we actually did a concrete example already. Believe it or not. We did earlier this problem that took up the whole board. So now here's the way you set this up. Using the fundamental theorem of calculus part 2. Using this guy, and this is basically going to rule our world for the rest of the semester. It's going to be this. You're going to forget that this is the fundamental theorem of calculus. You're just going to be like, well, that's what I do. The first step then is to figure out what big ass f is, and then I can just plug these endpoints in. So basically, what the antiderivative does is, by establishing that it's directly related to this g of x, the antiderivative collects the area from some point up to some other point. So if I want to know the area between, and actually it's from like negative infinity up to a point. So if I want to know from A to B, I just take the antiderivative of B, which represents all that area, minus the antiderivative of A, which represents all that area, and I'm left with the area in between, which is exactly what I want. So this integral symbol represents area between those two. The antiderivatives are really just collecting area. So if I take the difference between the two right ones, I'm going to be left with the area that I want. That's exactly what this is all about. So what is the antiderivative of this? We did that earlier. And the C's now, this is where people start to forget their C's, because you don't need the plus C, because of course we know that they're always going to cancel. Because I'm subtracting those. Not yet, but I'm just going to subtract. I want to go from 0 to 3. This is the conventional way to do this. To be honest, I actually haven't even looked at what way the book does it. Oh, sweet, sort of like that. Good. Because it all depends on the book here. And then all you do, the way you look at this is you plug a 3 in, minus plug a 0 in. So it would be that 1/4, 3 to the 4th. So we did this earlier. Minus 0. That's what you get when you plug a 0 in. This is what you get when you plug a 3 in. That's what you get when you plug a 0 in. And of course you end up with the negative 6.75 that we got earlier. So let's do another one. It's a little more interesting maybe. So don't forget what you're doing when you're doing an integral. You are finding an area from something to something underneath this function. Right? And when I say underneath, if it's below the x-axis, it's going to be negative. So what do you think? Try this one out. Let's see if I can throw a neat one at you. Wow. So come up with the decimal approximation. Go out to 3 places. And depending on your endpoints, that's what tells you if you need an absolute value or not. So how are you guys doing here? What's the antiderivative? From 2 to 5. This, of course, is where you just do that, really. Just fill it in. The biggest mistake I see is people, for some reason, forget to, that it's got to distribute. Right, don't make little mistakes like that. So just plug it into 5, you get ln 5 minus 25 minus ln 2 minus 4. So you get ln 5 halves, is that minus 25 plus 4, so minus 21. Where'd the 5 halves come from? Yeah, property of logarithms, it doesn't matter. You don't have to do it. So what is ln of 5 halves, roughly, minus 21? What do you guys get at the end there?
Negative 28.084.
0.5.
Nope. Try again.
Sounds a little bit too much, maybe, but it might just be my...
Negative 20.08.
Sounds better. Natural log of 1 would be 0, so if the input to the natural log is more than 1, then ln should come out positive. Does that make sense? Because it's positive, it goes from 0 at 1, and then after past that it should be negative. So I knew this should be bigger than negative 21, because this first part should be positive. So negative 20 point, whatever the hell you just said, sounds right.
20.08.
Okay. So far so good? So you can see we're going to have to expand possibly a bit how many functions we know the antiderivative of, because we want to be able to integrate all kinds of stuff. And it's going to require us to make up some rules for handling more complicated intervals. But let me do a couple more here real quick. What do you got, Jeff? Let's not do that. That would freak you. Let's say plus 2, sorry. I never made the claim that these integrals will actually work. There might be a problem with something. Here it is. So let me just say a word. You should be about done with this one, maybe. A word about this one. A function is integrable if it's either continuous on the interval that you're looking at, or has a finite number of jump discontinuities. So if you think about it, if I have a jump discontinuity, I have a function that comes along, and then it jumps, and then it goes along, and then it jumps again. The interval actually is not that concerned about that. It just finds this area, and it finds, this, so it finds this area, it finds this area, finds that area. I mean, the interval is not going to care that much about it. You're going to have to break up your interval along there, right? It's going to definitely be piecewise anyway, so you're going to know to break it up. Do you guys understand? So either your function has to be continuous, or it has to have at most a finite number of jump discontinuities, in which case the interval doesn't care that much. You just break it up, right? If it had an infinite number of jump discontinuities, that would be an infinite string of integrals, and that gets really freaky. So we won't go there. So what happened on this one? So this one does not exist, because this guy is not continuous through 0, right? At 0, it freaks the hell out. And again, the integral is summation of areas, and if I'm going to infinity or negative infinity, that gets really weird. Trying to add those together, that would be indeterminate, possible. What happens here? Yeah, good. So two things there. Negative cosine plus 2x, and I want to go from 0 to pi over 4. So I get negative cosine pi over 4 plus twice pi over 4 minus negative cosine of 0 plus twice 0. So I highly recommend doing that, parenthesis with the minus sign in the middle so you don't forget to distribute the negative. What's cosine of pi over 4? So you get negative root 2 over 2 plus pi over 2 plus 1 minus 0. And then you can give me a decimal approximation for that. 2.57. I don't know, I'm too tired. Is it 3.27? No, it'd be minus, Jeff. 2.5 minus 1.8?
Yeah.
1.7?
Yeah.
So yeah. Alright, I can think still. 1 point, whatever you guys just said, 1.7 something.
1.8.
Oh, that's close. Alright. Blah, 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 blah. So that would be integrating, and here's sine of x from 0 to pi over 4. So pi over 2 is where it would hit 1. And then I just up that by 2. So I'm finding this elevated area there. Does that make sense? So from sine from 0 to pi over 4, I kind of made it look like it reached its screw. And then lift it by 2, that's the whole area I'm finding underneath there then. Okay. So be careful about that. People get way too entrenched. You can actually do this. Find the antiderivative, plug a 2 in, plug a negative 1 in, you get a number that doesn't make a damn bit of sense. Because the function was discontinuous somewhere in that interval, you can't even do this process. It doesn't work. So you have
One more time while we know that that's discontinuous.
Say again?
Explain one more time while we know.
Because it goes from negative 1 to 2, and this is not working at 0. So 0 is in that interval.
Oh.
Can't do it. Yeah.
But right below that, you said that one.
This one's okay. So this is not infinite discontinuity. This is just a jump discontinuity. So it's sort of like, and I always look at this and think Mario Brothers for some reason, but you have something here, you find the area below that, and then you have, now it's up here, and now it's down there. Now you see why I think Mario Brothers, but, or not, if you don't play.
But because
So the integral won't care. But my intervals are going to have to be set up between A and B and B and C and C and D, but the interval just still eats it up, right? But I do have to break it up at those points. And it would be a piecewise function anyway. It'd be like, well, duh, I got to integrate each piece. Okay, so that's pretty good for tonight. That's plenty. Yeah.